I see you're back. Let's look at my headphone on the ground. Okay, so let's have a look at some of the spring stuff, but in a different context. Okay, so let's say you're a spring. You want to exert force on something in the opposite direction to the way that you've been stretched. You want to go back to your resting place, to your equilibrium point. And so any object attached to you, again, we're role-playing here, you are a spring. Any object attached to you is going to want to come along for the ride, given that you're the only force acting on that thing, the only net force acting on that thing. And so we're considering a situation where we have some mass here, where maybe there's a force of gravity and maybe there's a normal force, but those are going to balance, and so that the sum of the forces in the y direction is 0, but the sum of the forces in the x direction is negative kx, which is in fact going to be the total net force, which is ma. And note this x is a vector as well. And so let's evaluate this equation and see what we can pull out of it. Okay. So this is our nice little equation that the sum of the forces in the x direction, and again, this can apply in the y direction, but might be a little messier when we add gravity. So what we're saying is that we have a spring attached to a mass. Let's attach it on this side just for some balance here. This is my equilibrium point, and this is the displacement x. And I want to know about the forces at that point. Well, we know that ma equals negative kx. And from our study, our very preliminary study of differential equations, you'll note that this x has something to do with this a. If we can represent this x in terms of a function of time, x of t, at some time I'm going to be at some position, then I can represent this as simply the second time derivative of that function. So m d squared x over dt squared equals negative kx. And remember that this is an x of t. That's a function of time. And this function of time tells me, well, why do I care about time here? It seems like I'm just caring about position, but as we've noted before, this is actually going to move back and forth and back and forth and back and forth and forth and back, and whichever direction is forth. No one knows. It's an old word. And so what I'm going to look at here is maybe how I can represent the motion as a function like this, and then maybe I can come up with some sort of solution or some sort of interesting information related to maybe a period or how long it takes to go back and forth and the like. So this is going to be the main differential equation that we're going to be looking at, and we could solve this, but instead we're going to analyze this situation very broadly, because what we're really going to see here is something that's periodic in motion, and lots of things that are periodic in motion. Well, why not just try to represent this with some sort of sine or cosine wave? What do you think I should do? Which wave? Does it matter? If so, why? And if not, why not? Well, let's look at this in terms of cosine and see if it makes a difference. So I'm going to say that, well, the position over time, or the position with respect to time of this object, of this mass, I'm going to say it looks a little like a cosine wave. I'm going to say that at first it starts far away, and then eventually it goes close, and then eventually it goes far away the other way. And we get, if this is my time axis, and this is my x-axis, then as I plug in time to my function, I get a high value here, I get a 0 value, I get a value on the other side, and I oscillate back and forth. I keep going positive x, negative x, positive x, negative x. And so this seems to fit the bill. In fact, for our purposes, because I'm considering this image, it might be a good idea to go with cosine. But on the other hand, a cosine graph is just a shifted sine graph. And so I could shift by, whatever portion of a period this is, whatever, depending on the length of the period, or the amount of time of the period. And I can get to a sine version. And so really all I have to do is do a phase shift in one direction or another, left or right, to get back to my sine wave. And so I'm going to just start with cosine because it's reasonably simple. It's just as simple as sine. So what does a standard cosine graph look like? Well, a cosine function from this graph, if I consider this to be the A value, the amplitude, I know that I'm going to have an amplitude in front, and I'm going to say cosine, and then I have some arguments in here. And if you remember from pre-calculus, there's some argument with respect to time. You might see that with respect to angle. And then there's a phase shift value. There's a shift value. And so for us, with our standard cosine graph, we're going to say this is the angular frequency. We're going to say that's the time, and we're going to say that's the phase shift. And the values that we really care about here, that define the particular spring motion, are going to be this omega and this A, and potentially the phase shift. But just plug that in as necessary. And so this is actually pretty interesting. Because maybe we want to be able to figure this out without doing any fancy differential equation stuff. Maybe I just want to see what's going on here. And how could I do that? If I define my function, my spring motion, to be based on this position function, how can I get down to an acceleration function? Yes! Differentiation! I take the slopes of the slopes, and I get there. So, please, math teachers, don't kill me. Okay, so what is the derivative of cosine? It is negative sine. So I have a negative A sine whatever's inside, and then I have to use the chain rule with the omega, because time is the thing that I'm differentiating with respect to. So just for clarity, dx dt is v of t, which is a negative a sine omega t plus phi times omega. That value pulls out by the chain rule. And then the second derivative, which is in fact something I care about very much right here, is a of t, the acceleration with respect to time. And this is equal to, well, the derivative of negative sine is negative cosine. And by the chain rule again, this is omega times omega. And if I simplify this down and I bring it out front, I get negative a omega squared cosine omega t plus phi. These two combine into omega squared. Negative a goes in front. And that is my acceleration. And that's really kind of gnarly. Because we don't know what A is right now. I mean, I could theoretically figure it out and plug it in, and then I get my things. But it feels like we have some similarities between that line and the top line up here. In fact, I have exactly x of t. And presuming this marker works, what we can get is that A and that cosine omega t plus phi matches up exactly with x of t. And therefore, I could really just rewrite this let's say what we're really replacing. We can rewrite this as A of t is equal to negative omega squared x of t. Because A cosine omega t plus phi is x of t. And so now let's take just one more quick pass and see how this, we see that A is just related to how frequent my oscillation is, in a sense, with some modification and some complexity there, multiplied by my position. And so based on my position, my acceleration is going to be in the opposite direction. And let's see what this looks like when I actually plug this back in. So here we are, we're plugging in. Okay, this is not an advertisement. So M of, well, that is A of t, which is negative omega squared x of t, is equal to negative k times x of t. And, well, this won't find us x of t. In fact, we already are making an assumption about x of t over here. We're assuming that we follow this function. But what we're doing here is we're saying, okay, under that assumption, can I figure something out about this angular frequency? And from that, can I figure out something about the period? And so, in fact, yes, I can. So what I get is that the negatives cancel out. And let me do this on a different line so that I don't confuse any of you with my algebra. Okay, so I get, I'm going to divide both sides by m. And I'm going to take out the negative, and then I'm going to take out the x of t. So this, and this, all, so those underlying things get removed by algebra arrow. Via algebra, I get omega squared is equal to k over m. And omega squared being equal to k over m means that omega equals root k over m. And if we remember anything from hopefully earlier, but perhaps not, this actually is something we can use. I'm not going to use this arrow because it reminds me of algebra. But one identity that we have is that period equals 2 pi over omega. And I'll derive this in a separate video, really simple derivation. But in this case, 2 pi over omega is something we should know. And then we can use that with this value to say that t equals 2 pi divided by root k over m. That's just nonsense. We should really make that nice and pretty. That's really just 2 pi root m over k. This is our period function, our period equation. So what does this mean? It means that as my mass gets bigger, it takes longer to travel through my oscillation. And as my period gets smaller, or as my mass gets smaller, it takes less time. As my spring constant gets bigger, it takes less time. So if my spring is stronger, I'm going to be pulling faster in both directions. And so my period will actually be reduced. This will be very similar to what we come up with when we look at the derivation for a pendulum. Clearly, we see that. And we'll look at that also in another video. But important things to note, in this oscillatory motion, we're going to often be using periodic functions like sine and cosine. When we have a differential equation with our position and our acceleration, we're often going to model the position on that oscillatory function, that periodic function. And then when we substitute, we can get some information about how long it takes to move through the process. Now, to be clear, we're not necessarily going to be doing this all the time. It's something you should absolutely know, and there are certainly questions about it coming up. But the other thing is that oftentimes when we're solving problems with this type of system, we'll go based on energy as opposed to forces. And the energy values are actually pretty simple. The energy approach is really simple. So hopefully I confused you just enough that you think about it and come up with some questions. Good luck.